To start with security in BGP for network operators. This tutorial, as was already mentioned, is today we're going to speak of the way we approach security in BGP. It's divided into three parts: the morning session, then there's another one in the morning too, is more on delegate RPKI, and then this afternoon a lab where you'll have a hands-on opportunity to practice what you heard this morning. Before we start with the tutorial, let me tell you of what we have in parallel. In room 104, the DNS presentation and coordination of number resources, and in 105 interactive tutorial, how does LACNIC administer your internet resources and how could you impact on that. And so, as I said, we're going to talking about security in BGP, and we are going to do it jointly with Erika Vega. Erika, could you please join me here? Erika is a member of the LACNOG board. She coordinates the working group on routing at LACNOG, and she's part of the manners steering committee. So both of us are going to be in charge of this session. So let's give her some time to get our devices connected, and then we'll get started.
Hola, hola. Te vas a acercar. Me toca. Porque le pega el micrófono en la y suena. si me va a conectar, pero espera que no va a conectar. Me conecto por cable. El que ahí está bien. Este. Y en el TV no se ve nada tampoco. En los TVs tampoco se ve nada. Y están distribuidos todos. Sí, pero poner en los televisores de adelante. Bueno, ya, empiezo.
Vos me vas pasando. Bueno,
So let us start then with this morning's session. We'll be introducing the topic of routing incidents. We'll be introducing routing incidents and the main tools we have today to prevent route hijacking, particularly route leaks. We will also be having a session towards the end with a brief introduction to some of the topics, some of the more recent topics that have been introduced in the IETF and are now being discussed. These have to do with new proposals to try and improve routing in the internet. So let us start then. I will start speaking about what routing incidents are and what are the main routing incidents that we have today. The first is route hijacking. This is one of the most common incidents we have. We'll have of announcing non-authorized prefixes. This can be for two reasons. It can be either intentional or also an error in configuration. Normally, many of the route hijacking events are due to misconfigurations. For example, an announcement that it should not be published or inadequate filters and so on. But on other occasions, this is also intentional. So how does this work? How are the prefixes announced when these are not authorized? This slide shows, for example, that the autonomous system 65501 has a client that wishes to reach the address 2001 DB8FF00::20. If you look at this client is connected to autonomous system 65501, and to reach that address, they should do so along this path. Because the autonomous system that has the address 2001 DB8FF00/40 is this 655.110. 655.110 announces a /40 prefix and to 65502, and 65502 receives these prefixes and reannounces it to 65501. This is how BGP works. Now, what would occur so the client then forwards the traffic 65501 to 65502, and then this is forwarded to 655.110. But 65509 is announcing the prefix IPv4, and also this is also received by the two autonomous systems. Now, what would occur if all of a sudden autonomous 6 and 65509 starts to announce a prefix that is 2001 DB8FA00, but instead of /40, it's a /48. If there are now filters that have been configured, if we don't take into account all these aspects that I am mentioning, this announcement will accept the 65502, and because this is a route that 65502 has no way in which to figure out whether to accept it or not, will accept it and then publish it. And it will be published to 65501. So 65501 will have three routes. So this is so that they can receive the /40 and the /48. Because /48 is more specific, that is the one that we'll be using. So in that case, a detour of traffic is produced, so the traffic that should have reached autonomous system 65510 ends up being forwarded to 65509. And that is what we call a hijack or route hijacking. And why does this occur? And it could be intentional, as I mentioned, or a misconfiguration. If 65509 makes mistakes and starts to publish that prefix, and this is accepted by the others and is then propagated, then route hijacking takes place. Route hijacking might have serious consequences because the customers no longer reach a content site or whatever. And if the route hijacking is intentional, it can be even worse, because there have been cases of using these techniques to steal bitcoins or credentials, and also hijacking prefixes of networks that provide DNS services. So in that way, they carry out other types of attacks. So this is one of the most common cases. In a while, we'll be having a look at the statistics. And the other case is that of route leaks. Route leaks occur somewhat differently in most cases. These are due to misconfigurations. So in these cases, there are some basic rules that in general terms should not be made, should not be broken. So when you learn provider prefixes, this should not be announced to other peering links or to other providers, as you are aware. In internet, when the autonomous systems get interconnected, there are different relations between these. There you have a client, you have a major provider, the client forwards the traffic to that provider, and then there are peering links between two organizations that exchange traffic with one another and exchange routes with one another. But normally, when a provider announces routes, we should not re-announce these routes. We should not re-announce these to the peerings, but yes, to the clients. If we are a provider and we are connected to other larger provider that sends us routes, we should announce these to the clients, but not to the peering links, nor to any other providers. Now, the same happens with the prefixes we learned from a peering. In a peering, we have a relationships between two organizations that are more or less similar. One announces the prefixes, but we should not re-announce these prefixes towards a higher providers, because in this case we'll be establishing traffic through our autonomous system that we don't wish to have. So these prefixes, the ones we learn from a peer, should not be announced to another peer or to a provider, but only to the clients. In this example, 65511 would be an autonomous system that is a traffic provider from the two below. So as you see in the image, 65536 announces its prefix to its internet provider, and 65537 announces its prefix to its internet provider. And between one and the other, they have a peering link. So the two each announces its own network. You see 65536 announces 2001 DB8:10/40 to traffic provider and to the peer, and 65537 announces 2000 DB8:20/40 to its traffic provider and to the peer. Now, if we don't have any filters configured, 65537, once it receives this prefix, will do this. It is going to re-announce it upwards, and this is what we call a leak. This is with a prefix, but very often it also occurs that a provider injects a full internet table, a large amount of prefixes, so this makes the traffic begin to circulate through a third autonomous system. So when 65537 lets these prefixes go through, that traffic might start to follow this circuit. In this case, this is with one autonomous system only, but it would have more autonomous systems. This is something that will occur and will also affect not only the links of 65537, but is also likely to saturate this and have other consequences. So this is one of the other types of incidents of common routing issues. So when we have a look at the security incidents, which are the main security incidents globally and also in our region, we can see this information over here. This is from the Manners Observatory. Here we can see that the large majority of the incidents, which we see here, route misoriginations, which are the ones we call route hijacks. So this is an announcement from an incorrect origin. So if you have a look at this, there are peaks that go up to 1,000 incidents a month. This is from May 2023 through to May 2024. This is globally, and you see that there are peaks that are up to 1,000 incidents, and in the region we also have peaks that go up to 150 incidents in 1 month. Over here, the largest number is route hijacks. Then we have route leaks. There are practically no route leaks in the region, but you do see these globally. And one of the other things are the bogons, something that we didn't mention yet. Bogons have to do with filters more. So not publishing networks that should not be published in the internet. These are private networks. These are networks that are reserved for some reason or another, private autonomous systems and others. So these are bogons, prefixes that should not appear in the internet but are published nevertheless. So this is something what we don't discuss here specifically, because this is just about applying the anti-bogon filters in the announcements that you make and in the ones you receive. So with that, this would be avoided. This is not something that requires major explanations.
So they are configured just in any, and there are anti-bogons lists that you can find in the internet. But as you may see, most incidents are the route hijacking. A positive thing that is seen in the region is that the incidents tend to go down. And in that regard, the actions of operators have a lot to do, and the manners program, for instance, that has been quite successful in our region. Now, at a global level, on a global level, although you don't see in this chart, incidents have gone down too. They've been dropping, and that's why what's so important to adopt these actions. In this map, you see the countries ranking first in the routing incidents. Of course, Brazil, because of its size, will have the largest number. But now we'll see the top 3 countries. There, the chart shows you the references in colors. Brazil, 1,200 incidents. Argentina, 122. Colombia, 103. And then the rest follow. And there you have the months. To your right, you'll see both the number and the types of incidents that happened in the 3 top in the ranking: Brazil, Argentina, and Colombia. These are data of a study on routing incidents that we conducted from my R&D area last year. It was in the hands of Erika, and it has to do with analyzing the cases of incidents. And there's a lot of information, and we specifically address some cases more in further detail. You have the link there. These slides will be there on the website. You can find them there if you can't click on that, of course. So there are some peculiarities there. Brazil, although obviously it's a very large number. There are many autonomous systems and addresses active in Brazil than in the rest of the region. Because of their number, because of its size, of course it was expected to be larger. However, there are some differences, and that's seen at the bottom, that have to do with the peculiarities as to what are the most frequent incidents. In the case of Brazil, there's a high percentage of hijacks. The percentage, well, the route gets hijacked. That's the main type of incident. Now, if we compare that to Argentina and Colombia, you may notice that in Colombia, hijacks are not as common as in Brazil, 48.5% only. And in Argentina, it's 66 and 34% bogons. So what do we see in Brazil? Well, probably this has to do with the low adoption of RPKI that is much lower in Brazil than in the rest of the countries. In Argentina, hijacks are high too, but in Colombia, bogans are very high. Here, the ratio is the other way around, and you see that's what's missing there, or at least what we can notice is that there's a reduction of hijacks in their number, so that means that the operators are applying the RPKIs and the origin certificates, but there are probably some BGP issues that are failing to prevent bogus that would be even easier to avoid, to prevent from happening. So, speaking of routing incidents and the potential causes and the main statistics, what can we do to mitigate incidents? Now, I'll give the floor to my colleague, Erika, and she's in charge of this part of our presentation. Hello. Good morning, everyone. Welcome to our tutorial. Then here we are going to focus on giving you the introduction to actions that as network operators we can implement to start addressing these incidents. What are the actions that we have that are available? If we know how our network operates, we're going to be able to implement those actions with no needs of purchasing any new equipment, any new machines, just learning how a routing system works and being aware of the various mechanisms that have been developed with time to address incidents like this. That's what Guillermo was saying. So here, I want to talk about a regulatory framework that has been ongoing, that is called the manners, that is the mutually agreed norms for routing, and it shows crucial rules that as network operators we must implement to face these incidents. The idea of this framework is to be able to raise awareness about this group of operators of the mutually agreed norms for routing security, and to understand what our role is to respond quickly when an incident occurs. So this culture that is promoted will give us clear actions depending on the role we play in this internet infrastructure, whether we are clients, whether we are ISPs, if we are a transit network, whatever. And we must be aware of what are the actions that we must implement when an incident takes place, and what are the actions that need to be implemented to prevent it happening. So we must then be aware of these norms to unify the frameworks where we'll have clear ideas of the activities that we are going to interact, and we must be able to contribute to the resilience and security of the internet. Now let's remember that and routing as such is based on trust. So if we speak of BGP, we establish connection with our different peers, with the networks in some BGP sessions that are trust-based, receiving all the information we receive from other networks, and the other networks also trust what we give them and what they receive. So, as I was telling you, these frameworks will give us the norms, and they will focus on providing solutions to these three types of problems. The first is focused on the data relative to incorrect routing. There we can speak of the two cases that Guillermo was mentioning. The leaks, route leaks, hijacks. We already saw that these are all these prefixes that we announce, not clearly understanding our role if we announce that to the other networks incorrectly, and all the route hijack when we publish prefix not having the right of use. And then the all the traffic with IP of spoofed origin. These are attacks that target some machines in our network, and mostly, well, one of the services that is more attacked are the DNS services, for instance, and the other one related to the coordination and collaboration among the different network operators, the different networks that get interconnected to do something when some of these incidents occur. Now, Guillermo was showing you the statistics. There are some specific cases that occurred here in Latin America. As we see here, there are cases that, although they were solved quickly, maybe the incident got replicated in other networks, but something was done very quickly. However, there are some cases that took more than 12 hours to solve. So there, the coordination and collaboration plays a key role. Now, this program of mutually agreed norms for routing security, so far we have these 4 programs specifically for the actions that need to be followed by networks depending on the role. So we have the program for network operators where we have all the internet service providers, whatever their size, small, medium size, large, tier 1, all the network operators, including universities, private networks, and companies that manage with autonomous systems, so with their own routing, their own IPv4 and IPv6 addressing, routing services. So it's a program that definitely has more members at present. Of course, this is a global level, a global program. We have the IXPs that play a key role. So manners for IXPs. We're now going to see a specific case, a success where quite a large incident could be thwarted thanks to the actions by one of the IXPs. We have manners for CDNs and for cloud providers, and each has their own measures that can be implemented and that should be implemented based on actions that we are going to set up, that we are going to implement in our infrastructure, and that's about it. And the other program that was developed, that is by the vendors, the manufacturers, the vendors of machines for the network. So here we have, I'm showing the 4 actions prescribed for network operators. This is the largest program that we have in this framework, norm framework. So there are 4 specific actions that need to be implemented to mitigate, to prevent these incidents, specifically not to publish incorrect data or to replicate forwarded information. But in this tutorial, we are going to we're going to focus on filtering and the actions that can be implemented, anti-spoofing, coordination. This comes hand in hand with the action that we are going to explain later and what we are going to see in the tutorial, but we are going to focus a lot on global validation, the actions and what we are going to explain. We are going to show you a demo, and as the day later on, we're going to have another tutorial with our colleagues of NECBR focusing on the way the validation of origin works in Brazil. And this afternoon, we are going to have a hands-on lab focusing on this fourth action. So there, we have the program, we have the 4 actions for the network providers, and here we are going to focus on learning about this global validation tool. So here, I want to tell you that in manners, well, of course, we have these global norms that must be adopted by the operators in general, the ISPs, the CDNs, and the IXPs. It's also an open program. Not only can we participate as an organization, but also personally as individuals. There's a process for developing this framework.
So this process will help us to receive the feedback from the community, and those who operate the networks are ultimately ourselves. So when we implement these actions, we can see whether we note that there are any gains and we are avoiding these things, or whether implementing other actions we can also help the system. So this development process of manners is an open process. I'd like to invite you as a community to learn more about this framework. And this is the link that you have in the presentation, where you can read the proposal for a new process which will help you understand in greater detail what you can propose, how you can propose this, and how your proposals then can become part of this global program. So I invite you to participate. I remind you that you don't participate as an entity organization, but you participate on a personal level. So I invite you to participate here. So back to Guillermo now. Thank you, Erika. So we saw what the incidents are, we saw the statistics, we saw manners and the actions, and what Erika was mentioning is the basis that can serve to improve things. So following these best practices, as I was saying, we can improve routing security. Now, one of the points that we want to discuss today is how can we prevent these routing incidents that we were describing when we started. So what we need to know, and you will recall the first case, the route hijack, where an autonomous system started to announce a prefix and the others accepted that prefix. And why did they accept it? Because they didn't know whether that was a valid prefix or not, whether this was an announcement that was correct or not. So how can we determine that? So BGP doesn't establish that you have to accept something or not. Any autonomous system can announce just anything. And this also depends on the other side, whether they accept it, whether this is filtered or not. So how do we obtain information beyond our autonomous system? And this has to do with the fact that what we have to do is to filter at the entry. If we have a peering relationship between two autonomous systems of 65501 and 65502, let me remind you that when you announce through BGP, announce prefixes through BGP, you're affecting the incoming traffic. And when you receive prefixes, you receive announcements from the autonomous systems, what affects you is that outbound traffic from that autonomous system. In the case of autonomous system 65501, it clearly has filters that can be applied to the filters it does. So the bogons are avoided here. So you have to have the prefixes where you deny other prefixes that shouldn't be published in the internet. You deny private autonomous systems. You deny autonomous systems that shouldn't be announced. But there are other things as well. So normally 65501 will have its prefix list configured, and these are the ones that should be announcing AdWords and the autonomous systems to which transit will be provided. So if you more or less are clear as to how to configure filters in BGP, there is no major conflict. This is quite straightforward. So you can automate this list applied to all the routers, and that's it. But the problem is in the opposite direction. When I have to determine what I'm going to allow system 65502 to announce, what am I going to accept, what am I not going to accept, what I'm going to let go through, and what not. 65501 has no way to figure out what it should learn from 65502. Now, which are the prefixes that 65502 has, and what is behind it? What are the autonomous systems that are behind 65502? What are the prefixes announced by those autonomous systems? So how does it know? This cannot be determined previously. Sometimes this can be done by email. You have the LOAs, the letters of authorization, where 65502 sends a letter saying that it's going to announce that these prefixes or these autonomous systems and so on. 65501 receives this letter signed by who knows who. Sometimes they check whether this is the administrative contact, but there's no many ways of checking this out. It could be a PDF letter that is not much worth. It can not be used for automating, but that is a system that is very often used. Sometimes it's just a phone call. You say, I'm going to announce these prefixes. These are not very rigorous methods. So that is the key issue here that IRRs and RPKIs intend to solve, namely to have information external to BGP in order to determine this. So when we connect to another peer through BGP and when we receive announcements, we have a way to have to have a way to figure out whether we're going to accept these or not. So there are two ways that are used today to make this automatable beyond the ones I mentioned. These are the IRRs, the Internet Routing Registries, and RPKI, which is something that is more modern. So just think of these as external databases whereby a router, when it receives announcements from another BGP peer, can go and check against these sources whether this corresponds to what has been published in these databases or not. Now, who published this? The owner of these resources, namely those that have the IP resources or the autonomous systems. The Internet Routing Registries, we won't be talking too much about this, but these are some of the tools that have been used for this. There are a large number of Internet Routing Registries. The most famous one is the RADB, and replicates all the other IRRs. So each organization defines its routing policies in an IRR. For example, LACNICS, or in another IRR, RADB is the one you have to pay. But there are others where each organization that defines which are those routes that will be published and with which autonomous system. This will then be used by the others to check that once a route has been published, it has then been published by an autonomous system that declared that it was going to publish those routes. This is an example of a registry. This is from LACNOG. The first line is Route 6, that is the prefix, and the line where you read origin, the third line, that is the autonomous system that should publish this prefix. So basically, that is what you obtain with registries such as these that are published in the IRRs. The rest is additional information on which is the autonomous system that is going to originate a given prefix. So from there, you do have more information. If that prefix is published by a different autonomous system, it won't correspond with the information that is declared by that organization. So you might suspect that this is an incorrect announcement. As I said, I won't speaking too much about IRR. We're going to be focusing more on RPKI. The IRRs have existed since the 90s. They became very popular originally and then more in recent years. But they do have some weaknesses, maybe due to the number of years that they have been used, but also because that model wasn't as strict and as rigorous as it should be. Towards the end of the 2000s decade, work began to be done with RPKI. This is a new model that defines a public key infrastructure that is specialized and has been prepared to be applied to routing. How does this work? LACNIC, or a regional registry, assigns addresses to end users or to the ISPs or organizations in general. In addition to assigning the resources, and we speak about resources, these are IPv4 or IPv6 autonomous systems. And in addition to assigning those, it will issue a digital certificate demonstrating that those who receive such resources are the organizations, or that organization is the one that will be managing these resources. This digital certificate allows you to sign objects, and that is the entire issue, the key of RPKI. This is a digital certificate associated to IP resources and to autonomous systems, whereby you can sign objects. Which are the objects that you can sign? The objects that we can sign so far are the ROAs. I say for the time being because towards the end we see that there are proposals for new objects, but for the time being what we're interested in is about signing the ROAs. ROA are something similar to what we saw a while ago, the right objects in the IRRs. This involves defining the association between a prefix and the autonomous system that originated it. So that is why this is also called origin validation, because in addition to defining that association, there's a validation mechanism whereby a prefix announced by BGP is announced by the organization which is defined in a ROA. So coming back to this, the major difference with the IRRs is that although the information is equivalent because the route and route 6 objects associate a prefix and the origin autonomous system, in RPKI this will be even stronger because it will be digitally signed. And who's going to sign it? It's going to be signed by the organization that has a private key associated to this certificate that was issued to it by LACNIC, and only that organization can generate that signature. So this makes this a much robust mechanism. All this information is copied in public repositories and is then distributed so that the validators can use these, and that is where we have the origin validation mechanism. So to sum up, and so to repeat the mechanism, we have BGP, where any autonomous system can announce just anything. But then we have filters that are applied to the outbound prefixes, but we wish to apply to the inbound ones. We don't know what is behind those autonomous systems. So in those cases, we can use these databases, both the IRR and the RPKI. Just think of these as information that organizations generate, and you can then use this and say, well, if I receive something through BGP, I can check against these options, and if it's all right, I accept it, and otherwise I won't accept it. So basically, that is what we do with RPKI. Now we have two considerations that we can make for the case of Brazil, because this is a bit different to the rest of the region. We normally have the RPKI with resources. We have a trust anchor, which is the one that has trust anchor, that is the one of LACNIC, and that trust anchor delegates or provides certificates to the organizations downstream. Now here we can do a second type of delegation. In the case of LACNIC, most of the organizations directly obtain the certificate of the resources from LACNIC. Now in the case of Brazil, there is a second instance. LACNIC delegates the certificate to the certifying authority, to NIC Brazil, and NIC Brazil follows this process with its own organizations.
So we are going to have two ways RPKI operates. One is the hosted mode, where maintenance is based on the regional registry, the RIR, managed through a portal. And this is the case for most regions, except for Brazil, where users directly manage through the MILACNIC system. All the part of encoding, rollovers, etc., all that is done in the MILACNIC system, and the repository, well, the point of publications of MILACNIC, etc. So this is very useful for organizations that do not that are not too complex, that are rather small. The other mode, the delegate mode, an organization may have their own CA that will hierarchically depend on the registry. So NIC Brazil will have their own CA, and in turn, NIC Brazil will give the operators the possibility of having their own CA. And this is of use for organizations that have spaces of other RIRs, or that are larger with more resources, such is the case of the national registries. They use a protocol that is used to connect the up-down that is to communicate with the upper CA, and this was available to implement this. The delegate mode is what you'll see in the next session that is going to be presented by NIC Brazil. We just want to mention this here so that you may know that there are two modes. So let's go through things again. So we saw the routing incidents, the key ones that are hijacks and leaks, and bogans, but well, we're going to focus on hijacks and leaks. That's the part that is more complex. I mean, the more complex solutions. We also saw the best practices, and there I talked about the mutually agreed norms for routing security, the manners, and the mechanisms that we have, and knowing depending on the role that we have in the internet infrastructure, what are the actions, so what are the programs that we'll pick to implement actions? And also, please consider how you as individuals may get involved in this program to join the Manners program. And the mechanisms, and the last thing that we described were the mechanisms for obtaining information on the autonomous systems. Remember that, think it over. Think of them as databases where you, well, not you, but routers will have information to contrast the BGP announcements against them. IRRs and RPKIs. So how is this information used? So we remind those of you connected remotely that you can use the Q&A panel to write down your questions, and we'll answer them here live in the tutorial or through the chat if we run out of time. So Guillermo was explaining the IRR, that is the database that we use to indicate the resources assigned that we have the right of use and how we are going to publish it. So we already know that they exist. We saw them in depth. Well, we didn't see the details, but we're going to focus on RPKI. And Guillermo Cicileo Chicho will he talked about the ROAS, where we're going to explain to the other networks how to use the prefixes that we are publishing in the internet, and we're going to see an example. Here we have a simple example. It's a connection between two autonomous systems, two networks, each of which has an independent ASN, and each network has its IPv4 and IPv6 resources, and there we'll see what each of these networks has to do, what data, how to produce those ROAS to publish it to the other network. 65501 will explain to 65502 how they publish the information, and the other way around. So here we're going to see in the case of 65501 how they should create those objects, those ROAS. We have the first prefix, the IPv6, and it's a /8 prefix that we always need to consider when we create these objects is how we are publishing our prefix, whether we are publishing it summarized, if we normally have a prefix depending on the type of network we are. If we are a service provider, then the prefix that we are going to be given in IPv6 is /32. But if we are a smaller client, an end user, we are going to have /48 to publish in the internet. So if we are publishing that prefix, if we are deaggregating it, how are we going to indicate that maximum length? How are we publishing the prefix? Summarized or broken down? And there is something that we need to consider, and that is that in many cases, depending on the type of entity we don't have, for instance, an assigned autonomous system. We use the autonomous system of our ISP if we are an end user in many cases. In other cases, end users have their own autonomous system, and they publish their resources based on the autonomous system. And that's something that we must clearly understand to produce the ROA. If we don't have our own autonomous system, we have to generate that ROA indicating the autonomous system of our internet provider. And the same for the IPv4 prefix. So there we have those two ROAS created. And in our example, we have these two resources in IPv4, IPv6, indicating that in this case, we are not disaggregating it. We are publishing the prefix 24 and IPv6 48. and the autonomous system of origin 501, that is the owner of the resources. Likewise, autonomous system 65502 should create their own prefix for IPv6, IPv4, and we are going to do exactly the same. In this case, the prefix is not being indicated, and in origin they publish the autonomous system saying that they're the owners of the resources, and in this case it's 65502, and then we put this chart together with this information, and you'll see in the case we're speaking of routing, so in the case that the router receives this information, they're going to start understanding or learning it. So there we'll focus on RPKI. We already learned that there's a mechanism that will help us show the other networks our right of use. What should we consider to generate these ROAs, these digital certificates? And now we're going to focus on the infrastructure where we work with the RPKI, that is the validation of origin mechanism. And now when we talked about manners, I said that we would focus on the global validation action. Here you're going to see this validation of origin. You're going to see what it's all about and what the infrastructure contains. Here we have a topology where we're going to see what includes this global part and how we can see the RPKI mechanism as it's running. One of the main things that we have in the validation of origin infrastructure is we have the repositories of each regional internet registry. So you may know that we have 5 internet registries regionally, each of which is in each of these regions. For Latin America and the Caribbean, we have LACNIC, then we have the registry that is in charge of Europe, RIPE NCC for Oceania, APINIC and AFRINIC for Africa, and ARIM for North America. Each registry will have their own repositories hosting the data of the digitally signed resources, the ROAs, and there each of those repositories of the RIRs will have all those certificates. And to your right there at the bottom you see the repositories of each of those internet registries. These registries will communicate with each other when we have validation of origin infrastructure with something that we will call a validating cache. That the validator is a software that we are going to install in a server, and this validating server will request the ROAs that were created and will have this system that it should be located locally so that it will connect with the routers that we have in our BGP. And we learn about our routes and we publish our routes. So here we have the validating cache, and this validator in this case will communicate through the RTR protocol to that router that we have in the infrastructure.
Al router que vemos ahí, el routercito.
So this is the router that will be in that BGP session that resides with this router that we have in AES and 1, 2, and 3. This router will have the routing table that we typically know with any router, where we have all the routes and the routes that we publish, and it will connect with that validating cache. When it connects with that, you will add an additional attribute that we know in BGP, that will be the validation attribute. So there, in our routing table, we'll have an additional attribute. We're going to see how we see it. And that validating cache, as it feeds on the repositories, it brings the local information of the digital certificates of the ROAs. And that is taught to the routers where we have a BGP session, and this will add an additional attribute.
So in this way, at a routing table level, we'll be able to see whether the information we are receiving is a valid route, an invalid route, or a not found route, depending on the information received from that validator. All this information has to be learned by the router, where we have the BGP session, and at the level of that device, decisions will be made whether to receive the routes or to block these routes. So we see the three statuses. We have the routers that receive information from the validating caches. These caches start to prepare this table with the information of the received prefix, the prefix of origin as it was delivered, as it is then broken down. This is prefix 22, prefix 24, and the origin autonomous system. So this is a 22 prefix. It's broken down into a 24, and in this way it is being published through the origin autonomous system 65501. There are three statuses of validity that will be included in each update message received in the BGP. This will depend on whether these are valid. The main thing is that the information coincides with the two rules I mentioned earlier that we have to bear in mind. The origin AS should be the one that is entitled to use it, and how we are originating, what is the maximum length, if we're breaking this down, if we're publishing the entire prefix, or whether this has been broken down. If this meets this information, if this coincides, it will be a valid route. An invalid route is when this information does not coincide. If we create a ROA for resource 2000.10.112.0 with autonomous system 65501, and we then see that the 65502 publishes this route, this will be viewed as an invalid route, because there is a ROA showing that the only origin that can publish that prefix is 65501. If that route is received with different information, it will be considered an invalid route. So that is when we start to decide whether to block it or to allow the prefix to go through. And not found is the third validity status, as when no ROA has been created. So the information we have globally of the RPKI from all the networks that have implemented, we can see that in many countries, of all the traffic that we have of IPv4 and IPv6, a large percentage of networks show this as not found. So for these resources, no digital certificates have been prepared, these ROAs. So this is something we already mentioned. We are aware that a ROA is equivalent to a route or a Route 6 object, depending on whether it's an IPv4 or an IPv6. This is an object in the IRRs, and this is associated to an IP prefix with an origin ASN. So with that information, it is possible to check this with the routes received in BGP. Who have the duty to generate these rows? These are the resource owners. All networks that have an IPv4 and IPv6 resource should announce their ROAs in order to inform the entire network about the right to use this resource and how this is being published. And where can you create these ROAs? LACNIC members from Latin America except Brazil, Latin America and the Caribbean except for Brazil, they will be able to generate it through the MiLACNIC system. You can access MiLACNIC with your user name and password. You will then go to the RPKI section and see how you can generate the ROAs for the network segments that you have and how you are publishing these. So we'll be here throughout the entire week during this event, so if you wish to have some support to create such certificates, or if you have any specific question, feel free to come up to us and we'll be happy to help you. For those of you from Brazil, you will then have a tutorial to see how they use a system and how the validation system works in Brazil. This is in delegated mode, and you'll see the details later on. Now, an important thing is that in the past, those who didn't have their own resources had the option of end entities. These are end entities that don't have their own resources, but the internet provider has assigned resources to them so that they can publish these. So they depended on the internet service providers to generate ROAs. Now, since the month of April 2023, a new policy was produced in the policy development process of LACNIC. This policy states that those networks that have sub-assignments, that are these resources that are not directly assigned by LACNIC but from the internet service providers, can then create ROAs themselves through the MiLACNIC system. As I said, there can be organizations that have IP resources in IPv6 or in IPv4 but don't have autonomous systems. These organizations have to create their own ROAs, but they have to be aware through which autonomous system this is being published. Many organizations have this system, which we call the multi-homing system, with several internet service providers, different channels, and each internet provider has their own autonomous system. So to be clear about the fact of which are the segments that we are publishing, because each of these paths, and then generate the ROAs with that information, with IPv4 and IPv6, and this through the operator through which I'm announcing that route. Well, I already mentioned all this, how to create your ROAs, that this policy has to be respected, which is the origin autonomous system, and how is this published in a summarized way or broken down. So this is the information where you can create ROA. This is the MiLACNIC portal. In the RPKI section, you have the segments through which you can generate the ROAs, the networks that are publishing this, and include the information of the autonomous system through which you are originating this. And in the case of Brazil, we have a specific case whereby they manage their own resources, and this is done in a delegated mode. There will be a specific tutorial on this topic after 11:30 today. Let us now share with you a brief demo. You will have a console where we will be showing you how the queries are done, or how you can see the ROAs when we do something we do a query to a validator and we bring up that information. So I'll give the floor back to Chicho so he can take on from here. So what we wanted to show you is how ROAs are viewed once you have a validator. Just a minute while I share my screen with you. I hope you can
Sillos hay micrófonos para.
There are microphones in the aisles, and you can take part in the system, and this will allow us to see the examples. Now, first of all, this is a Ford validator installed in a virtual machine. So first of all, you can have a look at the configuration of the validator, which is quite straightforward. If you take a look at this, what you will see is a description showing the trust anchors and shows a repository where this information is stored. These are the 5 trust anchors, the global trust anchors of each of the registries. Today there is no one unique, one single RPKI anchor, but each regional registry has its RPKI root. And then you have the signature of the original self-signed signature by each of the regional registries. So additional information of where the repository is located. Remember that the cache validator, this is a Fort, which is one of the validators. So it will download the repositories of each regional registry, and these will be stored locally in the server. Here we can put a file where you store the ROAs once they have followed the entire cryptographic validation process. Let me share with you what the repository looks like. So you will note here where it says local repository, this is a local copy, and each of the stars are here. This contains all the cryptographic information of that repository. This includes a lot of information, but if you prepare a list with all this, you'll see all the information on the ROAs and the different components of the repository. We're not going to look into that in detail. But what I want to show you, which is more interesting from the standpoint of operations, is the ROAs CSV file. This file over here includes the ROAs, information on the ROAs, once these ROAs have been cryptographically validated. So there you will have the autonomous system, including the prefix and the maximum length for each autonomous system. You will have all the prefixes and the maximum length and disaggregation. So over here, you have autonomous system 45037. that has a ROA that was created for IP 93.185.144.0/20, a maximum length which is 32. This is creating a ROA. You will recall that the ROA has the prefix, the autonomous system of origin, and a maximum length of disaggregation. Now, why is there a maximum length? This is to prevent attacks. The attack we saw initially, the type of attack we saw initially, was publishing a prefix with a more specific length. So this led to a detour in traffic. So you say, well, this can be published up to /32 in this case, but the one at the bottom, this maximum 24. If someone would publish it as 25, it would be then ruled out. So I won't find an example here with a /20 or /21, but you can then specify a maximum, and then if one publishes this more specifically, imagine you have a /22 prefix assigned, and you don't break this down, you only publish this completely, or you publish it in /22s, but you know it won't be published as /24, so the maximum length will be 21. If you specify, or /22 rather, so if you specify a maximum length as 22 and someone publishes this as a /24, this will be then ruled out because it won't be valid. This list over here is a very long list. If you count
how many ROAs, it says it has 500,000. So it will all depend on when it ran. Maybe it's not fully updated, and you can find, for instance, I'm going to look at LACNIC's ROAS, 28,000. It's LACNIC's autonomous system, and here you have all the prefixes announced by LACNIC and the ROAS created. You may see that there are ROAS in IPv4 and IPv6. I don't know whether anybody wants to give us their autonomous system, and we can check that. Does any participant want to indicate the autonomous system of their network so that we can check it? Can you give us your name? I'm Luis Medina of Venezuela, 11562. Thank you.
Bueno, el 11562 tiene, una IPv4 que es...
The 11562, there you have 562.275.128.0/2024 and IPv6/32, and the ROA says that you can only publish up to /64, and then you have two IPv4 prefixes, and in all cases you are specifying 17, 20, 22, 024s. In all cases you're permitted with a maximum length of /24. So, for instance, this 17, this is a prefix /17, and they are saying that you can publish from /17 to /24. Any of those ranges can be published. It's valid. If anybody were to publish this address highlighted here, /22 would be okay, as long as the ASO is for your, that is the one the autonomous system of origin that originates the prefix, the first to the right, or to your left in the screen. So that is the autonomous system of origin. Now, if some other autonomous system were to appear, it will that the announcement will be invalid in BGP, and then the rest of the autonomous systems will have to see how they can handle that. And here, all the prefixes are being handled from the autonomous system. No additional autonomous systems of any other providers. In the chat, we have some autonomous systems, and Cesar Augusto Camacho Sierra says autonomous 271927. That's his autonomous system. So here too we have prefix 181.224.222.0/25. Well, they put a /25 too. They won't see it because most ISPs filter those under 24. But for some reason they created a /25, a ROA with a /25. And then you also have an IPv6 prefix aggregated in 48, and they created ROAs for some of those prefixes. ASN 6558. /6568, it also has several prefixes. Here it has a /17 with /24, one IPv6. It has /32, and you can publish up to /48. And other, here you have a 22 with a maximum disaggregation of 22. This is precisely what we were looking for, a prefix that is a /22, and you're not allowed to disaggregate it. If somebody were waiting for 23, you're not allowed. Here, you have 94, 95. Here they allow 94. There's a specific ROA for that. You see that 92, they only publish it as a /22, or they can only publish it as a /22, but there's a more specific ROA for prefix that would enable you to disaggregate it. I think that would be all. Yes, thank you to those who sent the autonomous systems through the chat. So, we're running short of time. The idea was to show you a bit so that you would see it in practice. And there are some tools. In many cases, we don't understand how we are publishing our prefixes. For instance, maybe if we are entering a new, we don't have a clear information of how new administrators are publishing. There are several tools that can help us visualize that. The looking glass. Guillermo showed you the Fort validator. That's a software validator that is installed in the server. We saw it in the scheme, the validation of origin structure. This software, this validator, has another part that is Fort monitoring. And in that tool, you can put the number of your autonomous system, and it shows you everything that is being published in the autonomous system. So tools like this, and then another one that is quite popular that is our BRIS Inforedes, where you can use those tools to put the information, and we're going to leave you some links to give you some useful tools so that you may see how the publications are being produced in your network. So let's go quickly through this. The validators, the fourth validator, let's see how it's used, how the consultation gets done. Well, the validator is the software that is installed in a local server that will connect with our BGP router and will deliver the information of the ROAS so that we can add the attribute in our BGP table. And here I'm showing you some of the most popular. We have the validator. Well, though here the Octo RPKI and the Go RTR that were developed by Cloudflare, one of the largest content developer network, and it has all the support system that is mostly used by the network, by the CDNs. Then we have the NL NetLabs Routinator 3000, and it's a version with a professional support, and it's very efficient in terms of RAM and CPU. It's quite efficient. And all these validators, you can download them. They are free, and you can install them in your servers depending on what you want to use. So that Ford validator is the most commonly used. We're together with Nick Mexico. We developed it with Nick Mexico. So it has the validator part and the monitoring part. So here I leave you the Ford validator and the link. And as I told you, it's developed in C. It's free of charge. It's for Linux and VXB, BSD, and usually the networks that use validation are the networks that have a lot of information. Usually the end user does not generate a validation structure, but rather of infrastructure. As the ISPs are the ones that generate the validation. There's validity structures to provide validity attributes to all the routes for decision making. With these root servers, and they can apply this function, this feature. So here we'll leave some useful tools that will serve so that we may see what routes we are publishing under what autonomous systems, how we are publishing them, if summarized or disaggregated, and based on that we can then generate the ROAS. And we have tools that will be used to visualize or to monitor the status of our network. If at any time we are generating a row that is invalidating our routes, or if at any time some other network is publishing one of our resources, we have a number of tools that can help us visualize this. Some of the two most frequent are BGP Alert. This tool helps us monitor all our BGP routes and the validity that we have with our RPKIs. There we leave the link. You can download it from GitHub. This tool needs to be installed in a server if we want to use it. But then we have another tool that is also free. It's open source. Well, it's Packet VIS. We don't have to install anything. We'll see it on the web. You enter the tool, you indicate the autonomous system that you want to monitor, and that tool sends you information by or through Slack or an email. You choose the means, and we'll give you the information. And if they find anything on a global level of the BGP, they will alert you. If you want more details about the use of these mechanisms, they are pay per performance, you can ask us. Those are free. You can use them in your network, and it will give you a broader visualizations without the need to generate more validity infrastructure. You just needed to be able to have one of these sources available.
Here you have more tools that will be very useful regarding documentation that link to MILACNIC, where you can generate the ROAs. Then we have tools such as Fort Monitoring LACNIC tools, where you can do queries on the ROAs or RPKI repositories or on IRR data, RDAP, WHOIS, which is one of the most used tools. Then we have another set of tools that can also help us. This is more at monitoring level in order to visualize the information of those networks with which we are interconnected to see which are the routes that they publish. So all these are open, both for prefix queries and for autonomous systems. We can use any of these tools. RIPE-RIS, one is Hurricane Electric, and we also have the QRadar tools. This will deliver a lot of information regarding the published routes, what are the incidents, and these are tools that you could use for your own autonomous systems. Then we have the LACNIC campus courses. All those of you who are LACNIC members and who are here, remember you have free access to these courses. The idea is that you take advantage of these courses. We have a whole set of specialization activities, and specifically for this activity we have the basic BGP and advanced courses, and the advanced course, one on BGP security with RPKI and the use of IRR. So all these will be open during the second semester this year. So please register to these activities so that you can take advantage of these very useful options. Then we have additional RPKI documentation that you can find on that link. Now, what we have seen so far is what we have here. What we have to bear in mind to create a ROA, these signing of the cryptographic signing of resources, and then validated how validation of origin occurs. We saw all the scheme, the structure of how to do origin validation, the structure, the validator, the repositories, the information we receive in our router with the active BGP session, the validation statuses. We saw which are the most frequently used validators and the type of software we can set up in our servers if we are going to be generating this validation infrastructure. And then, of course, the tools that I mentioned, which will be useful for monitoring the network and to obtain information as to how we are publishing our information. So far, that was the presentation. Are there any questions regarding this information? Any comments? Those of you who are connected remotely, thank you for sending your autonomous systems, and we look forward to having your questions. First of all, thank you very much. My question is whether there is some kind of use cases of these tools by an ISP. I don't know whether at regional level that an ISP that is already implementing this tool. At the RPKI level in Latin America, we are the region that has the largest adoption percentage compared to the other 4 regions. In other words, if I'm speaking at RPKI, there are a large number of networks that own their resources and have generated their ROAs. Then we have the other part, which is the use of the validation infrastructure, that in their infrastructure that have this validation. There are many ISPs that do this. I don't know whether you realize that I'm from Colombia based on my accent, but in Colombia we have major providers that do validation. We also have networks and education, for example, like the Renata, the academic network that does this validation in its own infrastructure. But we also have traffic exchange cases. Yes, the traffic exchange points all do validation and discard invalid prefixes. The content providers also do origin validation, and at present, if you connect with a CDN, it is likely that the CDN will ask you to create your ROAs to have that information. And what Erica was saying, there are countries that have about, I would say, 97, 98% of coverage with ROAs. So the announced prefixes from these 97%, a very high percentage, more than 95%, are covered by a ROA. And overall, if we look at the average for the region, and also globally, but particularly in the region, more than half of the announced prefixes in BGP have some kind of ROA that covers these. So you can know whether a prefix is valid or invalid in most of the cases, more than 50%. Now, what is the expected percentage? I would say slightly above that, maybe 70 to 80%. It's very difficult to have 100% of the prefixes covered because this does take some time. But there has been a very positive evolution, and nowadays the majority of the prefixes are covered by ROAs, and the majority of the major providers, the major ISPs, the content providers, and the IXPs already do origin validation. We should also be clear about the difference. The main thing is that we have to be aware that if we own the resources, we do a lot generating our own ROAs, signing our own resources without the need to set up any additional infrastructure. This is because many of the infrastructures, both regionally and globally, already do validation and are already monitoring the validation status. And it is not so frequent, but there are cases where you have networks that they include the validation status not found when no ROA has been generated for that route. So these are filtered out. So the idea is to have our entire routes validated and that we're out there without any issues. Yes? Hi, good morning. First of all, thank you very much. I would like to ask you 2 questions. The first question, when you showed us some of the signed ROAs with the autonomous systems, we saw that there was some that had prefixes that went up to a /32. The question is, what is the point of signing a prefix with a maximum length of /32 in the awareness that the carriers filters some of the prefixes with /24? And the second question is whether the announcement of lag haul /32 would fall under the ROA or this falls outside that scope. Well, precisely, that is one of the uses. The black hole communities that very often require 32. So regarding that, there are several methodologies or techniques in order to use the black hole communities together with an RPKI. But some of these cases, I estimate we'd have to ask each organization why they proceed in that way, but I estimate that very often this is linked to that, either to internal issues of their own networks or also to the fact that they can announce a /32 prefix without the need to create a ROA at the same time. So if you have to publish this with a black hole community, and then the provider does RPKI validation, then it wouldn't allow it to go through. So having a ROA will then allow them to publish it. So that is a concept. Shall we go on? If there are no more questions, are there any questions from the remote participants? No? All right. So let us now wrap up. I want that the takeaways are what we said previously, what is being used actively. More than 50% of all prefixes that are published today in the internet are covered by ROAs. This has taken some time. When we started out with this, there were very few. The work with the IXPs has contributed to this growth. It has contributed to the increase in the created ROAs. Also, the content providers that started to request this contributed to the fact that many networks would create their own ROAs. And what I want to leave as a take-home message is that this is what you have to configure basically in order to secure your networks. Like Erica was saying, if we have IPv4 and IPv6 resources, we have to create 2 ROAs to protect these resources. Now others will proceed to validate these. If we are a network with one single provider, or we don't receive prefixes from the internet, then we'll be focusing on the creation of the ROAs, because this is what provides the information to the other networks so that they can be aware if someone is hijacking one of our prefixes. So if, as an organization, I don't create my own ROAs, I have no way to defend myself. If I do create these ROAs, I give the other organizations the opportunities, the IXPs, the content providers, or other major providers, they now have the opportunity to check the BGP announcements against the created ROAs. So that's the main point. And I was saying we will now have a brief session on some of the new proposals that are being discussed. Now, why do we have new proposals? Why don't we keep this alone? This is because RPKI provides only a partial solution. This is origin validation, which is validating the ASN that publishes the prefixes. The IRR provides a similar solution that has potential to do more, but this is not used very much. Then it does have some issues regarding the authentication mechanisms. So there are some things that, based on what we have right now, cannot be avoided with RPKI. For example, in the case of the leaks, the ASN, the origin ASN does not change, it is preserved. So this would not be useful, because if we are validating that the origin is changed, we could avoid a hijack, but not the leaks. And in addition to that, if someone intentionally would wish to make an attack, they can falsify the BGP announcement in order to add an autonomous system. The one they wish, so they originate with another ASN, and then the origin ASN would change. One of the proposals we had is BGP-SEC. This was not very successful. It hasn't been incorporated by the operators. The reason for this is that BGP-SEC does have some issues in terms of performance and how this affects the routers, as well as the model as such of this proposal. And this is what we mentioned regarding the leaks. And we could then make a false path, something similar to what I described when I started, but this is no longer published in 65509, but I'm publishing this through the 65510. So I add it's as if I would add a new autonomous system, an RPKI cannot prevent this. So that is why these new proposals come up. So what are the other proposals we have? We'll have a look at some of these to avoid route leaks using BGP roles. And then there's an RFC, which is 7908, that classifies the route leaks. And this is very important because after this RFC, other proposals came up regarding this classification, namely what are the type of route leaks. And once these have been identified, we will be aware of what things we can allow and which not. So this came up regarding the BGP roles. ASPA is one of the things that is being discussed quite a lot. This is to identify which are internet providers and then to declare through the new object which are those providers that an organization has. This is something new. This introduces a new object. Then there are many more that I won't be referring to here, but these are included in the presentation as additional information. These are available in the presentation if you wish to check these out. So back to you, Erica. I will very briefly now refer to these two RFCs, RFC 7908. All these discussions come from the IETF. We have the RFCs, which have now become standards. And that RFC 7908 is totally focused as an informative RFC, where we can then see the list of the different types of route leaks. Route leaks are these announcements or the propagation of announcements beyond the scope that they should have initially. And this will depend on what we are publishing, if we are internet service provider, if we are client, if we are transit provider. So which are the routes that we should publish through each of these? This RFC, which was approved and published in 2016, this is an informative RFC, and this will define these different types of route leaks. And these are the different types that might occur based on the experience and the cases that have happened. So these are then is classified. We have these 6 different types of route leaks. And this is included in the information that you have in each case. The topology describes this, but this is the information that can be published regarding what should not be published. If you're a transit provider from one to another, which are those routes that we shouldn't be announcing in that connection. The lateral leaks or between peers, which is a type of information that should not be published. For example, from a peer to a transit provider, or a transit provider to a peer, and so on. So these are different types. So then we have that informative RFC.
And then we have this RFC 9234 that was a proposal of a standard of May 2022, and it seeks to describes a method to prevent and detect route leaks in the network routing using the rows of the update and open BGP, where we have the active session, and we'll be able to establish specific roles so that the routers may have an action, identify the role, and then decide on whether blocking the route or to allowing it to pass. This method, what it does is, we're going to activate these features, these RFC, in the router where we are publishing, and we will assign any of these. We'll have these roles: the provider, the client, a route server client, and a peer. And there I'll explain in what cases to use each of these roles, and it establishes what kind of relation those roles should have. So, for instance, provider and client, client provider, and route server to route server client, the other way around, or peer to peer. Here we add a new attribute that is the OTC, only to customer. Well, for instance, if we have this network where we see lateral autonomous system, we have peering, we have, for instance, 65501, 6502, another lateral autonomous systems. The clients will use these autonomous systems, and then we have the transit networks. Here, the autonomous system can publish the routes that they add to their lateral peerings. They can publish it with no problems, and they can also publish the autonomous system to their client customers in those networks. They can publish them, but that autonomous system should not publish or teach their networks to the transit providers. That should not be done to those customers. So if we start to apply, if we use that OTC attribute where the routers, well, depending on the role, will tell us whether it is activated, and when there's a connection, the routes will go through the peers and will block the routes. If it's a superior network, for instance, and here I want to talk quickly. Well, here you have more information, more documents, so you can look at that. But if you want to go more in depth, you can visit those links. And here I can give you an example of how to use this RPC. This was an incident that happened last year. Here we have two IXPs, one in France and the other one in Canada, Amigai. And these IXPs configured the RFC, establishing where the routers where they have the BGP and the attribute only to customer, the OTC. That is, that it adds the attribute to the networks, to the incoming networks, and they decide whether they publish them or let them pass depending on their attribute. In this case, we see a topology where we have a as 154.07024. Well, there you have France IX has this RFC that is active in its routers. This route doesn't have that attribute, but it adds it because it's a customer that's publishing the network, so it adds the OTC attribute to the prefix and publishes it. So in ASN 3804 and the ASN publish, and that they publish it to 5939. That should not happen. Those autonomous systems should not publish the information of the customer, of the autonomous system, of the IXP. We should not publish it. So there, they don't have the validation, but anyway, the route is allowed to pass. But then it gets to the Canadian IXP, and there it has this RFC role active with the OTC attribute, where they see that the route comes that attribute that should not be there, so it blocks it. So all along, all of the autonomous system, well, they use those networks that had implemented that attribute. They could block that publication of that attribute that shouldn't have been allowed to go any further. So this is an example And that is in the report where we show the statistics. If you want more information, you can go and check this. Well, and finally, we talk about ASPA, because this is something that you hear about. So, ASPA is new. It's being debated as we speak in IETF. It's an object that declares the relation of a provider with another. A provider declares who their providers are. The autonomous system, well, they say the autonomous systems that can provide transit. And with that, you establish a chain. For instance, here AS1 can say that AS2 is a transit provider, AS3, AS4. So then you can check that chain. And when you read the AS path, you should find these pairs. And each autonomous system declares that the one that follows is a provider. And if that's not the case, then they would block the transit. So you have some that go upstream, an upstream chain and a downstream chain, and then you'll see how the cheerings may not be covered like this. But usually this allows you to check it this way and this way to see whether the path is valid. Of course, this is just for information purposes, because you'll start hearing about it. Now, if you want to see that in greater detail, you can ask us. Or you can see it in the IETF groups when this is currently being debated. Well, so, at the end of the presentation, there are several slides more, but what we wanted to recommend is to create the ROAS. If you haven't created any ROAS, you are not protecting against potential hijacks. So please create those ROAS. That's a protection for you. If you receive publications of routes of more than one provider, you should implement the several routes of origin. And as Erika said, there are several validators. Fort is one of the most popular ones. And then if the routers support it, most routers already support RFC 9234. That will help you prevent leaks. If you are an autonomous system, you can implement it, and that's all you need to do. And then to remain updated with the IETF debates. So this is what today's session, this session included. So we wanted to thank you. So thank you for the participation. I hope this information that we gave you in this tutorial, I hope it was useful. We invite you to go to the next tutorials. We have delegated mode, RPKI. Our colleagues of NICBR will be here, and that will complement the information you heard. And this afternoon you'll have secure routing, and there you will have the possibility of actually using the router, the validator, so that you may see RPKI in action. And there you'll see how it works. Thank you. That's the end of the tutorial.